Hi, welcome to Parametric House, and in this Rhino Grasshopper tutorial we want to model a twisting tower or a series of twisting boxes in Grasshopper, and I'm going to teach you how to make this from scratch. We're going to use a series of rectangles which is going to define the base surface, and finally we're going to use advanced techniques to extract the curves. And as you can see, we can even distribute the boxes differently with this Graphmapper. I can change the distribution and change the height of the boxes by changing this Graphmapper. But before we start, if you're new to our channel, welcome, and consider subscribing because we have weekly tutorials on Grasshopper. And also, if you're new to Grasshopper, you can watch this tutorial up here, which is for the beginners and why you should learn Grasshopper and those things. And also, before we start the tutorial, if you want to learn the advanced lesson of this tutorial, which I'm going to also explain how to divide this into steps with defined thickness, and then put them on the ground and find the location of each of those boxes on the bottom. I'm going to put that in the Paracourse, so be sure to check out our course website, paracourse.com. Okay, let's get started from scratch and make this rotating and twisting tower in Grasshopper. First of all, what I want to do here, and let me explain the first steps. Just turn everything off. I'm going to start with 3 points and define simply 3 rectangles on these points, which we can control their rotation, their X and Y sizes, and then connect them with a simple loft. So let's just get started and go to this with the Bifocals plugin. And I'm going to go to the Params menu and pick up the point. Right click and select Set Multiple Points. And I'm going to put 0 and enter to find the word coordinate. And then you can use and hit the Control key, select that point. Be sure that the point snap is on, and then hit on the Control key, click on the point and bring it a little bit up. So we have the second one, and again, and that is going to be the third one. So now we have these 3 points, which is the center of those 3 rectangles. Okay, we can go to this curve primitive and use this rectangle tool. This rectangle is going to let me just connect this. If you connect a point to a plane, the input is a plane, but we are connecting a point. That is going to assume that this is an XY plane. Okay, so that is the trick. I guess I have to write this better. XY plane. Okay. Then we have to define the size of the XY for each of these rectangles. Because we have 3 points, let's go to the Params menu and select this gene pool. I'm going to select the gene pool, double click on it, select 3, maybe from 1 to 100. Okay, we need 2 of these gene pools, one for the X and one for the Y. Okay, and now you can see that it's going to change the rectangles. The problem here is that because we gave the point to a plane, if I connect a plane to this, you can see these planes. These are the planes. Let me just make them a little bit bigger so you can see them. Okay, these are the base planes that this rectangle is going to be drawn. But you can see the input of the X and Y is a domain. So when you give a number, okay, for example 20 to the input of a domain, it's going to say from 0 to 20. Okay, so it's going to start from 0. But if we want to put that as the width of this rectangle, let me just draw this here and explain what we have to do. If we want that point at the center, what we have to do is to, let's assume that this is the X direction. We have to say it's like 20 divided by 2 and minus 20 divided by 2. So it's like 10 to minus 10, and the overall length is going to be the width we need. It's also for the second dimension of the rectangle. So we have to fix this by going to the math, and in the domain you can construct a domain, and in the start and the end I'm going to right click expression, type minus x divided by 2, and the end is going to be x divided by 2. Let's just Control C, Control V that, and use these new. You can see that the x is okay now, but the y is not, so I'm going to also give that for the y size. And that's it. That's how you put the rectangles exactly at the center, and now we can control their x and y's. The next part is to rotate these planes so we can rotate the rectangles. You can either rotate them after we have the rectangles, or just professionally you can just double click and search for rot and find this rotate plane. You can also go to the vector plane and find it here, rotate plane. Okay, and let's just put that plane, let's put the point to the plane, so it's going to show you that it's an XY plane anyway. So remember that connecting a point to an input, which is a plane, is going to be an XY. Right click and define it as degrees. Remember that angles in Grasshopper is in radians, so I'm going to put that into degrees. And now we need also 3 number sliders for rotation. We can say rotation. I guess it's not going to change here because of the Bifocals plugin, but for example we're going to go from 0 to 180 degrees. Put that to the angle. Okay, so you can see that this is going to go to the first one, the second one, and the last one. If I change this, this is going to rotate the first one, the second one, and the last one. Here we go. Let's just rotate them. So now we have the base rectangles, and that is the first part. Let me just save this as a group so you can have the first part, and bring this a little bit out so we know we want to start from here. Okay, the next part is to loft them together. So I'm going to go to this surface menu, and from the freeform menu I'm going to use Loft and connect them together as a whole surface. Just turn everything off, and now we can control by changing the rotation, right? By changing the size if we want to. For example, if I want to go for the top, I have to change this one, and that's it. Okay, and if you want to change the location, you can simply just move these points up and down. That's how you can change the box, twisting box, which we can also have in Rhino if we want to use it in our project. But for now, we want to extract a series of curves from this loft. So let me explain how we can do that. And I'm going to use not a linear distribution, but a Bezier distribution of extracting those curves. Okay. First of all, you can use other techniques. For example, if I go to transform, affine, okay, excuse me, intersection, mathematical, contour can be one of those. But remember, when you see these 2 dots, it's going to be slow because it has to find it step by step. I mean, it's going to intersect it with a plane, then it's going to go to the next one and till the end. So it's a little bit slow. So if you want to use this contour, you can pick up the first point, and let's just go to the sets and use this list item to pick up things. And let's just pick the first index which is actually going to be the first point, and give that to the point. The direction is going to be the Z, and then you can just give this a distance. And if I give this a 5, you can see it's going to intersect this box with a series of planes, which is 5. The default is in meters, 5 meters. You can change it anyway by changing this, going to right click unit setting. You can change it, for example, maybe centimeters is going to be fine. Nope. And then we have this 5 centimeters of this. It's something like a thickness for these boxes, right? But for now, we don't want to make this a little bit slow, because you can see by changing the box, it's a little bit slow. It has to calculate the contours. I'm going to show you another technique, and we're going to talk about this in the advanced lesson in the course. So if you want to learn more about it, you can enroll in our course, okay? So a faster way to get results is to convert this loft. You can see it's like a polysurface, right? 4 NURB surfaces connected together. So what I have to do is to explode that and work on any of these NURB surfaces to extract the U direction, right? To extract the boxes. That's the fastest way of how you can change the box and also extract the curves. Let's go to the surface first and deconstruct the B-rep. Remember that that is exactly the same as explode in Rhino. So I'm going to just give that to the loft, and we will have that grasshopper 4 faces, and let's just check that out. Okay, now we can go to the curve. In the spline you can find this iso curve, so I'm going to just pick up this, give it here, reparameterize. Remember, we have to reparameterize, so it's like from 0 to 1 and from 0 to 1 in the UV direction. And now we have to give it a UV point. This technique is really useful if you want to extract a series of curves from a polysurface like this. You can go to the vector and construct a point and give that to the UV point. And remember that this X, Y, Z coordinates, we have talked about iso curves and evaluate surfaces. Let me put a tutorial up here if you want to check it out and know more. But for now, let's just change this X coordinate to U and to V, and we don't need a Z coordinate, so I'm just going to put that like this, and we have to give this an input. For example, if I give this a number slider between 0 and 1 for the U, you can see that this is extracting this from the U, and this is for the V. We don't need the V direction. We have to work on the U direction, right? So if you want a constant distribution, you can simply just use the range. And again, if you don't know about range, I'm going to put a tutorial up here, check it out. But for now, the default number of the domain of a range is between 0 and 1. And it's going to divide the 0 to 1 to 10 steps, right? If I give that to the U, you can see it's giving us some output. But there's a problem. You can see that the curves is not on all 4 polysurfaces. The reason here is that we have 4 base surfaces, right? And 10, for example, 11 UV coordinates. So what Grasshopper does is that it's going to go like this. The first UV point is like here, 0, 0, 0, is going to go for the first polysurface, right? The next one, which is like 0.100, is going to go to the second polysurface. The third one is going to go to the third one. And the fourth is going to go to the last polysurface here. So it's actually something like, if I draw it's like this. Then, because we have the fifth and the sixth until the end, and we don't have the fifth polysurface, it's going to assume that all of this is for the last polysurface. This is a long list in Grasshopper, okay? Grasshopper, by default, is working on the long list. So how can we fix this? A technique is by grafting one of these inputs, okay? If you don't know about flatten, graft, and those things, I think that this tutorial up here is really great for you to watch. But for now, if I graft the points, because one of those inputs is in groups, you can see that like a group, and you can get rid of those zeros by just right-clicking and simplifying that. Okay, you can see that now we have 10 groups here, but the surfaces are not in groups. So that's going to multiply that. It's like 10 groups multiplied by 4, and the output you can see it's like groups under groups. It's like that, okay? And it's also going to extract all the curves we need. So let's just go to the Params menu and connect to the U curve. No, it's the V isocurves. We can just turn everything off. And now we have these here. Okay, you can see how fast it is. We can change the steps of the range, maybe from 3 to 30. And this is really faster than the contour tool. Okay, here you can see that's just dividing it. Now, a good thing about range is that you can also use it combined with a Graphmapper. So I'm going to use a Graphmapper, which you can find in the Params menu. Okay, I guess that I want to show you here in the Params menu in the input. Let's find it out. The Graphmapper, here it is. And by giving it to the Graphmapper, it's actually between 0 and 1 by default. Okay, right click, and from the graph type, I'm going to use this Bezier distribution. That's the best graph type you can use to change the handles. Here you can see how easy it is to change the distribution from linear to non-linear. That's it. That's how you can play with this. Okay, and it's really fast, and you can see how fast it is. Okay, now we again have an advanced lesson here. Because the surface, if I just turn off the graft here and turn the graft on the surfaces, you can see that we have groups here, right? I'm just thinking how I can explain this easier for you. Let me just simplify that so you don't get the zeros, and let's just talk about the groups. I guess that Param Viewer can help you to understand this. Okay, and let me decrease that, so we're going to go to a real lesson here. Yes, okay, I used the simplify to get rid of those zeros, and just take a look at this. Here we have like 8 groups, like 0, 0, 0, 1, 0, 2 to 0, 7. Then it jumps up to 1, 0, 1, 1, 1, 2, until the end, right? So this is something, a group underneath a group. You can also right click and draw the trees. You can see it's like 4 different trees, which is the 4 polysurfaces we had. Each of those polysurfaces has those points. If I graft this input, you can see that this is going to 1, 2, 3, 4, 5, 6, 7, 8 groups, and that is because we have divided the 0 to 1 to 7 parts, which is going to give us 8 parts. Okay, so that's the difference between grafting which input you want. So now what we have to do is to just bring down the groups. What we want to do is to use a tool called Shift Path. Okay, this is the tool. You can find it in the Sets, Tree, and Shift Path. Okay, it's going to bring a path 1 step back. You can see the offset is like -1. It's going to break down one of the groups. Okay, and now you can see that we have here simply 7 groups of 4, right? So based on which one you graphed here, you can see that now we have 4 groups of 8, or you can have 8 groups of 4. But we need the 8 groups of 4. Why? Because, let me explain here. This is going to be good. For example, I guess this is going to help you understand it. The group 0 is going to be this one. Let's go to red. And the 4 part is like this one. 0, 1, 2, and 3. Again, for the next group, for example, if we go to 6, it's like this group. And it's like, if it's rotating, perhaps this is the 0, this is the 1, this is the 2, and this is the 3, right? And when we have the groups of 4, it's really good because we can just join them together to have the rectangles. So that's the trick, because if I bake this, you can see that we have separate lines here. And if we go to the curve and use this join curve tool, it's going to give us the rectangles. But if we grafted this input, you can see it's going to have 8. Let me explain this. This is also beautiful in Grasshopper, the data management. It's like this. When we graft another one, it's like 4 groups. The first group is this one. So this is the 0. And we have 8. So it's like 0, 1, 2, 3, 4 till the end, right? So that's the distribution. The changing of the graph is really important. I'm going to put it back here, and now we have the curves back. You can see that we have 8 groups, but we can just flatten this so we have all the curves, which is 8 polyline curves, the rectangles here. That's the next step. Let's just make this a group so you can understand that we have to take the next step. I hope that this part is really not confusing you. It's really easy, and we just use a couple of components to make this possible and make the distribution. Let's just increase those parts. And the last part is to just give them a little bit of extrusion. So how can we find the extrusion height for each of these rectangles? Because they are different. I'm going to teach you a trick you can use here. Okay, let's go to the curve section, and in the analyzers, I'm going to pick up the endpoints. You can also find it here. And you can see that's going to pick up the start and the end. Basically, the start and the end is the same, but for now, we just want the start. That's it. Why do we extract the start points? Because each of them has a z, a height, right? Let me just put a panel here. And basically, the height is really simple. The difference between the z of each of these is going to be the height of the first curve. The difference between these two is going to be the second height and till the end. So let's just extract the z. Go to the vector and say deconstruct point this time. We have the z's. Now we have to just find, the first one is going to be this number because find the distance between these two numbers, right? What we want to do here is to go to the math, and in the operators we can find this relative difference. It's a great tool. Let me just make this panel a little bit smaller and connect the output so you can see what's happening. Okay, so it's going to give you, like, the difference here is like 2.9. The difference between here is like 3.3, something like that. The difference between here is like 4, something near 4, and the difference here is 4 till the end. But we have to get rid of this 0, so I'm going to just get rid of that by going to the sets, and in the sequence I'm going to use the call index to delete the first index, right? I mean, we need the first index to be deleted. Get rid of the title, and you can see that we don't have the 0, and we are good to go. Okay, now we can extrude them. We can just connect a surface to the curves and convert them into a series of surfaces. And now we just need to extrude them. So I'm going to extrude. You can find it in the surface, free form, and here we have the extrude. Okay. And now we have the Z direction. And we have to give that to the numbers, okay? And what's going to happen is going to extrude based on the height. That's correct. But there is a problem here. Just let me explain. Is that the last one is not right? Because we don't need this number. This number is not correct because it is the difference between the last Z. Let me just explain here. So it's like 23, but we don't need to extrude the last one. So you can just get rid of that too by using the call index. This time it's not the first one which we want to get rid of. We want the last one. So another technique you can use, right click, reverse to put that first one to 0 and then reverse. So the output is going to be like the first one, the second one till the end, right? And that's it. That's how you can make the twisting boxes. And just let's take this a step forward and give this some preview. I'm going to go to the display section and give this a custom preview so you can see the colors. I usually give it a swatch. Whatever color you want, just play with the swatch. And I also give that a surface analyzes wireframe to extract the edges just for visualization purposes. And we have this color here. That's it. That's all we have to do. We just get rid of the last one. We don't need the last one to be extruded. If you want the last one to be extruded, we can have the last one here, okay? But anyway, I just turn this off. And that is all we wanted, okay? Let's just turn everything off. And now you can play with the boxes. So you can change the twisting part, right? Just twist a simple twist. You can play with the sizes here. And you can also increase the number of parts you need. This is really fast. If you wanted to use the contour, it's really slow. So I usually use this technique. And if you want a simple distribution, just go to graph type and put it to none. You will have a simple distribution. And so that is how we can have this series of twisting boxes, and then we can just simply bake them in Rhino. Here you go. You can have that in Rhino. Okay, that's it. Thanks for watching this video. Remember to subscribe and like this video. And if you want to learn the advanced lesson for the course, you can also enroll in our course and learn how to convert these into a series of curves, which is the location of each of those boxes on the bottom, right? You can find the curves. I'm going to teach you a technique which you can find these and put them into dashes, and it's better for fabrication. Thanks for watching. See you next time. Bye.